Now that I've done all 85 things to get the meeting started. Okay, so yeah, let's see. So last class we went through heat curves, and then in office hours I kind of like tinkered around with solving one of the problems where you're like, you take 2 cubes of ice and you put them in a glass of water and it heats up and stuff. And I really like those problems. I did such a bad job of explaining it though, and I don't. Maybe I'll post an explanation video for it. What would I say about that? If that shows up on an exam or something, it won't be as ridiculously challenging. I guess I'm much more concerned with understanding what's going on during normal phase transitions and stuff. Although I do really like those problems, but it's hard for me to want to test you on it when I botch them myself, although there are only 20 people in office hours. I guess what I'm saying is, for now, just focus on the stuff that we went over in class and all of the problems, I would say, except for the one where you have I mean, obviously, if you want to learn it on your own, which, I don't know, you guys probably have a lot going on. You're probably not super interested in learning about ice cubes melting in water. Let me see. Let me find the problem so I can tell you which one. So let me figure out the chat one.
Number 17, problem set 1.
Number 17, problem set 1. There we go. Yeah, so if you go to unit 1, there's problem 17, and there's some ice melting in water. Am I in the wrong worksheet here? Yeah, anyway, problem 17, there should be one about some ice melting, 2 ice cubes, you put it in a glass of water, etc. And then trying to figure out what happens there. Those problems are really not, they're just long. But yeah, if you want to work on that, go for it. But I wouldn't focus on that if you're just struggling to keep up with things. But try and move on to something else. The likelihood of me giving you that on an exam, I guess, is low. And if I do happen to give some problem like that on an exam, I'll probably give you guys a heads up on that the week of the exam. So for now, I just let that go. Try to focus really hard on understanding the heat curve stuff. That's my advice right now. Okay. Yeah, so let's move on from heat curves then, now that we have some basic understanding what's happening at these phase transitions. And let's take a look at some phase transition diagrams. So these always stand out to me, phase transition diagrams, because these always stand out to me because when I took general chemistry, I didn't quite get them, and then I took physical chemistry, where you get into more detail on this stuff, and I still didn't get them then. And it's because I just looked at them and thought they looked hard, and then just didn't want to learn them. But then when you actually take like 10 minutes to learn them, they're really not that bad. So yeah, so the typical way that these things look is, for a phase diagram, is you'll have pressure, and then you'll have temperature, let's say, and then there'll just be a bunch of squiggly lines on here. Yeah, if you look in the problem set that we gave you, unit 1 problem set, you'll see we have one in there for like diamond, which is kind of interesting because it has some allotropes in there. You know, there's diamond, it's for carbon. There's diamond and there's graphite and stuff. But more commonly, you're looking at like water or carbon dioxide or something like that. Let's see. So, 1 second here. Okay. Yeah, so they look like this. And like you can see why, as an undergraduate at least, I was like intimidated by this, because like, what the hell is this? It's just a bunch of squiggly lines. But the deal is, so let's say, let me try and at least get it approximately. Let me try and get one because it looks kind of like water. So they're actually not that bad to read. They're totally, or more or less, qualitative. There's no real calculations to do on these. And they're a nice way to kind of summarize what happens as you go between pressure and as you change pressures and you change temperature, et cetera. The way to read these is, let's see, the way to read these is that these boundaries just tell you, the boundaries themselves are the phase transitions. If we ignore those for now, so we'd have a phase, oops. So those are the phase transitions. If we ignore what's happening at the phase transition, we see that there's three kind of distinct regions. We have this region where you're in the ice form, the water form, and then you're in water vapor. And so you've got all three phases represented on this phase diagram. And what you can do is, if you're given a particular pressure, so let's say, let's say you're at normal atmospheric pressure, would be like right there. And so that would put this at 100 degrees Celsius. But if you're given a particular, one way to look at these, if you're given a particular pressure and temperature, you can say what phase the particular substances that you're looking at will be in. So, for us, we're at 1 atmosphere. So, like the phase diagram, you're always going to be looking right here, unless you're like way high up in the mountains or something. You're generally right around here. And so the phase transitions happen like you would expect. Solid ice, right? You're in ice below 0 degrees Celsius. You can see my diagram's not perfect, but below 0 degrees Celsius, you're going to be a solid. And then as you get above 0 degrees Celsius, now you're going to just liquid water. I'm just going to write liquid water since obviously all of these are water. They're just in different phases. Right, so pay attention to that. So if you've never seen one of these before, if I'm at 1 atmosphere, all this graphic is telling me is that in this temperature range, so I'm not moving up or down at all, I'm just at 1 atmosphere. At this in this temperature range, from wherever I'm at here, minus something or another, out to, which should be 0 degrees Celsius. I could fix that. Something like that. Out to 0 degrees Celsius, right? I'm just going to be in ice. So this is part of your normal experience. It's just being able to like read these things. So as I move past that though, so let's say between here and here, I'm ice. As I move past that, now I'm going to be liquid water. And I'm going to be liquid water across this temperature range. And then finally, once I hit 100 degrees Celsius, which I know is the phase transition for water, that's the boiling point, now I expect things to become water vapor, right? So now I'm in this kind of bottom piece here, the part that's blocked off down here, once I get above 100 degrees Celsius. So at normal atmospheric pressure, all this diagram is telling me is what we already know, which is that below the freezing point of water, what we think of as the freezing point of water, we're going to be at ice. That's what this whole chunk of this diagram down over here tells us. So as long as I'm here, I'm going to be ice. As I go past that, now I'm going to be liquid water because I'm in this part of the phase diagram, this upper part up here. And then as I keep going, now I become steam. Yeah, I will post answers at some point. I try to avoid posting one of the questions in the chat, and I get a lot of pushback from you guys on this. will there be answers posted? Yeah, we'll give you guys the answer at some point before the exam. I know it's frustrating to work on problems when you don't have the answers, but you learn more, even if it is really annoying. Yeah, you learn more. If you have questions and like you really need the answer to it, post it on Piazza and have somebody else answer and kind of dialogue with it. The problem with getting answers to problems, I'm getting a little bit off of this phase diagram, but I think we got through the first part. The problem with posting answers to problems, at least what I've seen, is that students will see the answer and convince themselves that by looking at the answer, I think I even posted this in an announcement, that by looking at the answer, they have now solved the problem. And it's not like you're doing anything wrong, it's just how brains work. And then you think that you've learned it, and in fact, you have not learned it. And so there's like this confidence that comes with looking at the answers that's not real. It's like when you're in class, this happens to me a lot, when you're watching somebody else explain something, especially one of the lecturers who kind of does the same lectures every year, and so it's very polished. You get this feeling of like, oh, I really get this, because the delivery is so smooth, but you don't actually understand it. They understand it, and you're just sort of like connecting in with that. And then the test comes, and you're like, oh shit, I have no idea what's going on. So just that's sort of the push there. So you should have an idea of whether you're getting the problems right or you have no idea what you're doing when you're working them, and just ask questions on Piazza, and then we'll give you the answers as the date gets closer. Or during office hours or something, we can work through them. Okay, but so we've got this phase diagram here. The question we were going over in class, what was the actual answer? Because people are getting different answers. I don't know, because I didn't actually work it out. Post that on Piazza, though, and let's come to some sort of consensus there. Certainly the TA or somebody can help with that. You should, I guess what I feel like is, obviously you ultimately do want, because since you're beginners, you do want to check your answer and make sure you're right, but like you should, if you are not confident in your answer, it's much more useful in terms of learning to go back and double check your work and sort of question your assumptions and look for mistakes that you may have made if your answer disagrees with somebody, than to just be told exactly what you did wrong. And it's a really awful way. It's the awful way that we kind of have to learn as humans. It's just like this kind of struggle but that struggle piece is really important. So just trust me on that as you're feeling really, you can direct your frustration at me as your instructor, but trust me that it's in your best interest to not have the answers easily accessible. All right, so anyway, so we've got this phase diagram, and at 1 atmosphere, everything behaves exactly as we want. And so there's equations that you can use, like this Clausius-Clapeyron equation, or equations related to vapor pressure and stuff, to calculate how boiling point will change at pressure. So one thing to note, I don't know if we've talked about this explicitly, but like, I'll write it down. At different pressures, the boiling point changes. So boiling point, I think in my lecture I talked about this, but boiling point, the boiling point is dependent on the ambient pressure, or whatever pressure is above the liquid that you're dealing with. The boiling point is literally the point at which the vapor pressure, which is the sort of evaporative pressure that happens from the liquid, is equal to the pressure that's being exerted on top of the liquid. And so if you decrease the ambient pressure, you decrease the boiling point of the fluid. And in some sense, you can think of it as like the atmosphere is sort of pushing down. If I've got a glass of water here, part of what's keeping the water together, are the intermolecular forces between the water molecules. But the other thing that's keeping the water from just going in the gas phase is there is this pressure, this sort of weight of the atmosphere on top of it. So this would be the pressure pointing down. And so there's this other pressure that we're aware of now, which is the vapor pressure, which is sort of pushing up against the atmosphere. And the boiling point is when those two things become equal. So the vapor pressure itself is like a property of the substance that's based on the intermolecular forces. So that doesn't change. Let's see, is that true? that doesn't change with the pressure. And so as I decrease the pressure, the vapor pressure of the fluid is staying the same. And so the boiling point of the fluid will change. So what I'm saying is like this force, as long as I'm not changing the temperature, the force being exerted up sort of onto the atmosphere, it's kind of a way to think about it, isn't changing. But if I decrease this pressure at the top, eventually, as I decrease that, since this force isn't changing, that's going to lower the boiling point. The vapor pressure and the boiling point are, related, if not identical in some sense. Anyway, so all this kind of complicated stuff I'm talking about down here to try and understand it microscopically comes out really nicely on this phase diagram. So if I change the pressure here, do we need to know the Clausius-Clapeyron? Because the lecturer said no. I think there was a Canvas homework question where we needed it. Oh, yeah, if maybe one of the LEs or something, it's in there. I'm not going to test you on the Clausius-Clapeyron equation. It might just be kind of residual in the LEs from because one of the other instructors made that. But yeah, there's not that much interesting stuff we can do with it. The main thing that we're trying to understand here is just that what you should be understanding conceptually is that there is this dependence of boiling point on pressure. If you have to bang out like what that exact change is, yeah, that's when you go to the Clausius-Clapeyron equation. You can see it's kind of a messy equation, and it works a lot better if you know some calculus, or there's a lot more to think about if you know some calculus. But we're obviously, I don't want to go over that. So anyway, all right. So ignoring the Clausius-Clapeyron equation and just looking at this conceptually, as I go down, let's say, and now I'm at like, I don't know, I'm just making this up, but 0.8 atmospheres here, or some lower, let me just call it something lower. So let's say I'm at a lower pressure. So I've gone down from 1 atmosphere. So this would be like as I get closer to outer space. So I'm traveling up. There's less atmosphere above me, so atmospheric pressure becomes less. Atmospheric pressure is like literally the weight of the air on top of us. So as you get higher and higher, the atmospheric pressure gets less and less until you get to like, outer space, and then the pressure is essentially 0. So I'm going down in pressure. So like I'm climbing a mountain or something. What do I expect to happen? As the pressure goes down, these phase changes, these boundaries for these phase changes that we've drawn over here, they say the same on the diagram, but for us, the temperature changes for the phase transitions will change. So yeah, the way I have it drawn here, whether this is true or not in real life, I don't know, but you can see that the ice to liquid water phase transition doesn't change that much. And that's probably true in general. You would expect the pressure to have less of an effect on the solid. But then as I move, so it's still around 0 degrees Celsius, but then as I keep moving to the right, what do I see? I see that the liquid, when I get to here, I see that the liquid, damn it, I see that the I see that now in order to get from a liquid to water vapor, that's happening at a much lower temperature. So that's happening right here. So as before it was happening at 100 degrees Celsius, now it's happening at whatever that is, like 30 degrees Celsius or something. So as the pressure drops, what I see is the boiling point also drops. And the phase diagram just tells me exactly what that is. So if I actually had the axes here labeled, with actual notches so you could see quantitatively, you could just look at this diagram and very quickly say, well, at whatever this pressure is here, like 0.5 atmospheres or whatever, I know that my boiling point is now going to be, whatever this temperature is, like 30 degrees or something. So the Clausius-Clapeyron equation you could use to calculate essentially one of these graphics, right? I could use the Clausius-Clapeyron to, at least for the part where you're going between liquid water and water vapor, I could use it to calculate and plot this nonlinear relationship between pressure and boiling point. I'm saying, let's not worry about that. Let's just learn how to read these weird ass diagrams. So the main thing though to recognize here is that these things change, right? So now that one hasn't changed very much, but this one has. And then, yeah, once you get outside of that, there's not really anything to pay attention to. Then you're just at water vapor. But the point at which you become water vapor is now lower. So if the pressure decreases, essentially what you're doing is like, you can imagine that if you're kind of walking along that line there, as I move down this curve, the pressure is dropping, as is the temperature of the phase transition. Pressure dropping as is the temperature of the boiling point or whatever. So that's kind of what's happening along those little lines. So the only other interesting thing to note about these, I understand the boiling point gets affected if pressure changes, but what about temperature? What happens if you change the temperature? I understand the boiling, let me think about that question. I understand the boiling point gets affected if pressures change. So the temperature doesn't, I don't know how to phrase this exactly. Yeah, I guess if you change, So I would say in general, you're not usually worried unless you have a very specific, yeah, the temperature reads left to right for sure. Maybe down here is like -20 or something. But generally speaking, the way to read these particular diagrams is that you're looking at the pressure, and what happens is the pressure changes and how that affects the temperature of the phase transition. I'm trying to think of the opposite question, which is like the temperature changes. How does that affect the pressure of the phase transition? That doesn't really make sense to me. It depends on what system you're looking at. So right now, I guess the system that I'm imagining is like you're just on Earth. So you're in this open system where you're kind of under atmospheric pressure. I guess what I would say is, what happens when we go down the curve? Yeah, I can repeat that. I guess I will say that the temperature, one way to think about the temperature that's not represented on the phase diagram is that as you increase the temperature, you increase the vapor pressure of the fluid. Right, so the temperature increases the vapor pressure, but that's not, for me, I don't really think about these diagrams as being a good representation of that. Yeah, the only thing I was saying about the moving around on the curve is, these boundaries here, like if you're thinking like, so you have this, if you look at the Clausius-Clapeyron equation, you can plug in a bunch of numbers and say, okay, if I change the pressure to this, now I've got this particular temperature for the boiling point. But if you're just trying to understand qualitatively how that works, all you have to really look at is just this leg of this curve. Right, so I'm ignoring the rest of these boundary conditions over here, but this here is exactly like if you were to take the Clausius-Clapeyron equation and plot pressure as a function of temperature, this is what you would get, is this curve right here. So this curve on this simple diagram tells us exactly how the temperature changes with respect to pressure. So if I'm here, for example, right, my pressure is really high, that tells me that at high pressures, my boiling point is going to be higher than what I am used to experiencing in atmospheric pressure. And then as I kind of move down, those two things kind of change together. So I'll notice that here, right now, my pressure has gone down, but also the temperature has gone down. And then as I continue to move, I see that again. So the temperature has gone down, but the pressure has also gone down. And that whole trend just continues down. It continues as you move along the curve. So my temperature goes down and my pressure goes down. So what you're kind of saying really is, what we're saying is that pressure and temperature let's see, we would say they change, increase, yeah, proportionally. And so what I mean by that is that, as I increase one pressure, and let me say pressure and boiling point actually. So pressure and boiling point change proportionally. So all that means is that I increase the pressure, the boiling point also increases. The reason I avoided the Clapeyron equation is just because, as you can see from this, it's not a linear relationship. You know, it's in the weird ass curve, and that just makes the math a lot messier. That's why we end up having to use calculus or something for it. Calculus is good for curves. But it's not a linear relationship, but it is proportionally, it does change proportionally. And that's all we're really saying. And that's what this curvature effect basically says. So right, if you didn't have this whole diagram and you were just looking at a plot of, if you were like, well, you know, somebody was like, represent how the boiling point changes as a function of pressure, you could plot pressure versus temperature, and then you would just draw a curve like this, which would just say that, right? And you know, this is kind of more what we're used to seeing, which is like, so this would be each of these, this would be the boiling point of that fluid. This is kind of what we're used to seeing. It's just like a single line plotted on a vertical and horizontal axis. And this graphic up here, right, it captures that, but it also captures this other information that we're interested in, which is what happens with the solid and going through the other phase transitions. And I'm sure there's equations that can describe that as well that I'm just not familiar with because I don't do PChem. Okay. So, yeah, as you increase the temperature of a fluid, you do increase the pressure, the vapor pressure of that fluid as well. It's one of the things that's hard to kind of wrap your head around is like when we talk about pressure, especially when we're talking about boiling point, usually we're talking about these systems where they're sort of, well, it's confusing as to which pressure we're talking about. Are we talking about atmospheric pressure? Are we in a closed system, et cetera? And we try to be kind of specific about that when we ask questions here, when we ask questions on the exam or something. But yeah, if you increase the temperature of a fluid, you are going to increase the pressure. And you have experience with that. If you've ever left like a water bottle out or something during the summertime, when you open it, you can like hear the pressure getting released from that bottle, right? Or if you have like a can of hairspray or spray paint or something, it'll say like, don't leave out in the sun. And that's because as you heat that, you increase the pressure inside of that. That's more of like a PV equals nRT situation. I guess it's a vapor pressure situation though. If you have some of it, that's still liquid. But for phase diagrams, particularly for these, the way I think about them at least is that you're thinking of the pressure as being like the external pressure that's pushing down on the fluid, not the pressure exerted, even though they're related, not the pressure exerted by the fluid so much. So as I change that pressure on the outside, you know, like I give the example of traveling out in space, but you could also like put something inside of a vacuum chamber, you're going to change the boiling point of whatever the substance is that you're looking at. The interesting part about these curves, or one of the more interesting things about these curves, is that if you go down, so up at the top here, above this point, we sort of experience, this is kind of how we experience the world, at least with respect to water, which is that we go from ice to water vapor. But what happens when we get down here? So now we're at low pressure. So if we're here, so below this, so we're in this range here. So we're at really low pressure. So let's say we're right here. What's going to happen now? So as I travel across, I go through this phase transition. But what phase transition am I going through there? I'm a solid. But now I'm going directly to a gas. Oops, wait, that's not my color for gas. Should have used more different colors, but yeah, I'm going directly from a solid to gas. I'm skipping this liquid water phase. And so what we're seeing there is sublimation. Yeah, solid to gas without crossing liquid, exactly. So we're subliming, the solid is now subliming. And so the most common example of this at atmospheric pressure for us is dry ice. So dry ice goes immediately from a solid to a gas. And that just, if you look at the phase diagram for carbon dioxide, that becomes really clear that at 1 atmosphere that happens. For water, that's not our experience. Water goes from liquid water to gas, but if you pump the pressure down and decrease the temperature, it'll go directly from a solid to a gas. And this is not something that's super familiar, but if you have like so the most common application, or a common application of this technology, is for those like you ever like space ice cream sandwiches. So when astronauts go out into space, the payload, whatever, any kind of weight that's added is extremely expensive, because you have to carry this stuff out into outer space, and you have to use these enormous rockets and stuff. So the food that they give them, they dehydrate. It also preserves it, which is nice. But the food they give them, they dehydrate. But if you just dehydrate, like let's say an ice cream sandwich, like put it in the oven, what do you expect to end up with? Just sort of like this weird kind of gummy mess. But if you decrease the pressure on the ice cream sandwich, so if I have my ice cream sandwich, so if I just try to like dehydrate this, like, not a very good ice cream sandwich, but bear with me. Maybe if I put some color in there. So anyway, if you heat this ice cream sandwich up in the oven at atmospheric pressure, so like let's say I heat it up to 100 degrees Celsius, so I'm boiling off all the water, and I'm at 1 atmosphere, what I end up with is just like this, just kind of crappy mess, right? Like maybe it kind of looks like an ice cream sandwich, but it doesn't look very appetizing. But if you've ever had one of those, like you can buy them, these space ice cream sandwiches or whatever, if I take it and I pump the pressure way down, so let's just say very low pressure. So, I'm at like a tiny fraction of an atmosphere. I've got like a pretty strong pump on there, and I'm going to bring the temperature down to like minus 20 degrees Celsius or something. Now what I've done is I've moved into this part of the phase diagram up here. So now I don't have to go through that liquid state. And because I don't go through the liquid state, what I end up with is that the solids from the ice cream, like all the proteins and stuff and sugars, they're just kind of left behind intact. And the water molecules that were inside of the crystal, like in the crystalline lattice of the ice inside of the ice cream sandwich, just sort of sublime off, right? So I get something that maintains the structure that I had, but it has no water. The structure is retained. The like place where another place that you end up seeing that is like when they make drugs. If you have to take, like if you have an injectable, for example, like I don't know if they do it with insulin, but if you've got like 2 milligrams of drug there, that's not very much. And so what they'll do is they'll dissolve it in a whole lot of water, and then they'll sublime off the water, and you get this really fluffy kind of thing that dissolves really quickly. Oh, where you end up seeing this a lot in food is like, now they sell these things like, it's called like just blueberries, and it's fruit and it's crunchy. They've used this technology to get that, right? They've decreased the pressure and the temperature on that to remove the water, so that your blueberry that you end up with is not dehydrated in the sense where it's like this kind of like gummy mess. Like if you try to dehydrate it at home, it's like this really crispy kind of weird texture that reminds you of a blueberry, but like something's a little bit weird about it. Anyway, so that's what's going on there. That's kind of the application of that technology. But in order to do that, you have to have this big vacuum chamber, and you have to decrease the temperature a whole lot. But that's pretty much it. So the other things that are interesting on this diagram, so the boundaries, so a couple of things. The boundaries represent the phase transitions. So the most obvious one is like when I'm going from liquid water to water vapor, this right here this is the boiling point, right? So this is how I expect the boiling point to change as the pressure changes. And the same thing is true here. If I'm a solid and I'm changing the pressure, this is the melting point and how the melting point changes with respect to pressure. I've got this interesting thing that can happen down here where now I'm subliming the solid directly to a gas, and we kind of talked a little bit about the applications of that. And then right here is the triple point of this whole thing, and this is interesting only in that it's the point at which you can have all three phases existent simultaneously. So if you think about here, you like along here, it's like I'm at the boiling point, I have two phases. I have liquid and water vapor, right? And they're in equilibrium with one another. If I'm over here on the ice to liquid boundary, I again have two phases. I have ice, I have the solid, and I have liquid water. So, you know, when I'm at equilibrium there, I have those two. The triple point is just interesting because I have all three. You know, I can have water vapor, I can have ice, and I can have liquid water there. So it's just like you're in equilibrium, but you're in equilibrium with all three of the different phases that you can have. Let's see, the only other thing about, well, there's other things to talk about with phase diagrams. The only other phase diagram, I have to pull one up. The only kind of other interesting thing to talk about with phase diagrams, I think that's what I'm about to explain. Yeah, okay. Yeah, so there's another point. I don't know if water goes through it. If it does, it's at a much higher temperature. But if we look at a phase diagram for something else where the critical point is reasonable, like carbon dioxide, this diagram is weird. Here we go. So I don't have the phase diagram for carbon dioxide memorized. Yeah, so we'd have the same kind of thing. So we're looking at CO2 here. We've got pressure, and we've got temperature down here. Okay, and then this is, of course, the liquid. You should be able to, and I think we have a problem like this where you just have to kind of identify what's happening in the different phases. It should be intuitive as far as why these line up, right? At high pressures, I expect things to be solids. At high temperatures, I expect to be gases. You can label these without having them labeled for you. They always follow the same pattern. But yeah, so we've got their triple point, which is right here, which is not super interesting. You know, one interesting thing might be that if we were to actually plot where 1 atmosphere is for carbon dioxide, we see that we go immediately from, if I'd drawn the damn diagram appropriately, let's see, solid. That's in megapascals. Actually, I can just, let's just call this 1 atmosphere. So what you would expect to see on these diagrams, right, is that 1 atmosphere, which is what we're experiencing right now, is that we go immediately from a solid to a gas. And that's what you observe if you ever buy a chunk of dry ice. You know, it doesn't go to a liquid. But if I play around with the pressure and the temperature, I can move along the phase diagram, for example, and get to the more familiar scenario where, you know, at higher pressures, I would go from a solid to liquid carbon dioxide and then ultimately to a gas. But I bring up carbon dioxide not because, well, one, because, you know, maybe it shows that phase diagrams are different for different materials. But sort of the cool thing about carbon dioxide is at high temperatures and a particular pressure, we get to what's called the critical point. And so above here, like in this region, let's say, you have what's called a supercritical fluid. And so supercritical fluids are interesting because they don't they're not liquid and they're not gas. They're somewhere in between. They're indistinguishable. And I don't know the exact like super physics of the details, but um, they have properties of gases and liquids, which makes them really useful. So um, unlike a liquid, which has like a lot of surface tension, uh, a supercritical fluid does not. And because it doesn't have a lot of surface tension, it can penetrate into materials really easily. So, if you've ever taken water and uh, you like pour it on like a sheet of paper or something, it kind of beads up and it takes a while to soak in. Um, and when you have a supercritical fluid, you don't have that problem. It would be like if you poured water on the paper and it just immediately absorbed in. And so the use of that though is that it's really helpful for extraction. So I think I talk about this in the lecture video, but um, one common place that you see those extractions, or probably the most common place, is that they used to use organic solvent for this, but now they use supercritical CO2 is in coffee. So you take your coffee and you put it into a chamber and you put carbon dioxide in there, and you would look at one of these phase diagrams and say, okay, I'm going to put it at the appropriate pressure to where I'm in this supercritical fluid zone up here. So, some sort of high pressure and high temperature. And so now you have this thing that penetrates. It doesn't have much surface tension, so it penetrates into the coffee beans really deeply and easily. And then you so you let that happen. So now the carbon dioxide's all dissolved in and sort of dissolves out all the caffeine into this thing that's not quite a liquid and not quite a gas. And then I can turn the pressure back down, and then all of the caffeine and stuff just sort of crashes out of this supercritical fluid. And so I've effectively extracted it out. The normal way that you would do that is, so like if you don't use a supercritical fluid where you can just like adjust the pressure and very easily get it back out, is to use a solvent. And so we used to use methylene chloride, which is this nasty organic solvent that, at least for me, because I used to work in the lab, burns my skin. And you would flood your coffee beans with that, and then you would remove that solvent and you would just keep pumping on it and trying to pump it off by decreasing the vacuum. But it's always hard to get like some of the residual methylene chloride off. And it's probably not enough to actually be toxic, but nobody wants to be, it just like feels icky, I think, for people to have to know that their food was processed in that way. So supercritical CO2 is much cleaner. There's no carbon dioxide, for example, left in the coffee bean. And even if there was, who cares, right? We're breathing it out and breathing some in every time we breathe. The more modern application of it, now that the marijuana industry is kind of picking up as state laws relax, is people buy these big supercritical CO2 rigs. And when you want to extract out, you don't get just pure THC out of it, but you get rid of a lot of the other crap inside of the plant. So you get rid of chlorophyll. You get rid of chlorophyll and like sugars and all this other kind of nasty biomass. There's a lot of crap in the plant you don't want, right? Like the membrane for the plant and stuff like that. And so I guess you get together a whole bunch of marijuana and you flood it with this supercritical CO2, just like you would for coffee. But now the waste product there is like, once you've leftovers, like the plant, you throw that away. And then when you flip the pressure back down, what precipitates out is like reasonably pure, like THC with all the different cannabidiols and stuff in it. So it's really commonly used there. Anytime you're doing an extraction, generally, you can use supercritical fluid for it, and it makes it easy, and it's nice, and it's a clean way to do it. And potheads in general, or people who smoke marijuana, are like very, like, they want to feel like their drug is clean and not processed for a variety of reasons. I feel like they're more intense, like that Whole Foods kind of crowd are like more intensively anti-chemistry, which is it's fine. There's nothing wrong with that. Anyway, so that's where if you get like if you're buying like pot extracts or like gummy bears, it's probably, or somewhere when you're in California and you're of age and it's legal, and I'm not saying that you should or shouldn't or judging you for it. That's where it's probably coming from. Somebody somewhere along the way probably extracted with supercritical carbon dioxide. And so if you're like going into chemical engineering or something, I don't know what the federal laws will look like in 10 years. No one does, but it seems like it's going in that direction. That industry of marijuana it just seems to be growing ridiculously large, and there's going to be a ton of jobs in it. So it's sort of an interesting place to look at. Although I don't know, I don't think either of the presidential candidates is very pro-marijuana. Joe Biden was very anti-drugs during his tenure in the Senate, and I don't know what Donald Trump believes in, but I don't think he gets stoned very much. All right. Anyway, I digress. I feel like Bernie Sanders, he'd probably legalize marijuana, but I don't really know. Certainly Andrew Yang would have. Yang Gang. I actually saw Andrew, I don't know how to pronounce his last name, but I actually saw Andrew Yang talk at UT when I was in graduate school before he was a presidential candidate. He didn't have a lot of charisma, I guess. I didn't watch him in the debates, but he didn't have a lot of charisma. I guess he made some money off of I forget how he made his money. Oh, he's an interesting guy. It's weird to see somebody before they become semi-famous, though. He was just, I could have walked up to him afterwards and talked to him, but I wasn't really interested in doing it. Now I kind of regret it, Who will win the election 2020? I don't know, man. I don't know. I think it depends on what happens with the pandemic. I think if the economy, usually I think the economy predicts the presidential win pretty well. And if the pandemic keeps up, it's going to continue to kind of crash the economy, even though the stock market isn't reflecting that. So my guess would be that Trump will lose, but you never know. It's hard to beat the incumbent. So yeah, I have no idea. I'm not really deep into politics, but I would say if it might feel like, especially in Austin where everyone is fairly liberal, it might feel like there's no way Trump could win. But if you go and look at the polling and stuff, it's not like people like him. He's got 42% approval rating. That's like half the United States almost. So don't let your sampling bias sway you into believing one way or the other. Oh, we're out of time. I kind of ramble on about Donald Trump. Let's see. We have modules due on Sunday, September 6th. Yeah, so the way it's set up is, that's going to get me off. It's so easy to get me off topic. But the way it's set up is the modules from this week will be due on Sunday at midnight or something like that. So it's meant to be you get them done during this week, but let's say you've got crap going on because you have other classes or whatever, we're in the middle of a pandemic, so you don't get it done. It gives you some time over the weekend to get them done. That's how it's set up. So you should try and keep up with them during the week, though, so you're not trying to kill yourself on Sunday getting through them all. Anyway, you guys enjoy your weekend. I will send out an announcement. You should ramble more. Thank you. You don't have to tell me that. I'll do it naturally. But let's see. I'll send an announcement kind of saying what we're going to do on Monday and what problems and stuff we'll work on next week, and post some more lectures probably. But you guys have a nice weekend. Make sure to find some time to relax and try and rejuvenate. Anyway, it's good talking with you guys. I will see you then.